All right, it looks like it's 11:30, so I'll go ahead and get started here. So I'm here to talk about ductile iron manufacturing. My name is Mattie LaPrade, and I am a manufacturing engineer at American Cast Iron Pipe Company. We make ductile iron pipe, so I know a little bit about our process and a little bit about other people's processes just from being in the industry. I'm an FEF alumni. I graduated from Virginia Tech in 2017 and attended the CIC back in 2016. So I'll go ahead and get started. So first, I'm just going to kind of cover what exactly is ductile iron. So it's got a base iron that's very similar to cast iron, but this base iron has been treated with magnesium or cerium or even lanthanum to produce a nodular microstructure. So here in the top right hand corner, you start with the flake graphite on the left, and that treatment is really what makes it the ductile iron and changes that flake graphite into nodular graphite. Typically, people are using ductile iron because it's a very low cost to manufacture. It's got better ductility and machinability than cast iron and other materials, and it's also got good castability, so you can make tougher shapes and a good toughness. Typically, you see ductile iron being used in water and sewer lines, which is what we do here at SIPCO. Automotive components, gears, pump housings, and then there's a long list of other places that ductile iron is used. Moving on to a basic process overview. So making ductile iron is not very different than making other castings. You melt your material. You sometimes have to desulfurize. It's listed as a step in the manufacturing process, but it's not always that you have to desulfurize. You're looking for a sulfur value that's lower than what typical cast iron is, so sometimes you will based on your melt method. Then you treat with magnesium. You pour your casting, and then depending on the surrounding microstructure that you want, you may have to heat treat. So I'll talk about those steps throughout the next few minutes here. So there are two primary melting methods that are used, typically used within ductile iron manufacturing. That's cupola melting or induction furnace melting. So with the cupola melting, you have raw materials that build up in the stack, but one of those raw materials is coke. Coke has a lot of sulfur in it, but it acts as a fuel, so it's necessary to cupola melt. They inject oxygen into the coke, which provides heat, melts the raw materials, and it comes out the bottom, and it's a continuous flow. Typically, if your slag basicity isn't just right, you will have to desulfurize with cupola melting, so that's one drawback, but it is a continuous melting practice that can provide a high tonnage rate. So there are ductile iron manufacturers out there that use cupola melting, and typically if they're not using cupola melting, they're using induction furnace melting, and that's a batch melting system. So they'll fill that furnace up, melt that furnace, dump it out, refill it up with solid raw materials, melt it, dump it out, so on and so forth. But something that's good with the induction furnace melting is that you don't have that high sulfur content, and you have a little bit more control over your tap temperatures, which is very important for your magnesium treatment. So your silicon content, there are a few main elements in ductile iron. That's carbon, silicon, your sulfur, and then your magnesium. Your silicon content will vary based on your treatment method, but I'll talk a little bit more about that in just a minute. So as mentioned before, you might have to desulfurize. There's a few primary methods of desulfurization. The cupola slag can actually desulfurize the material as it drops through the slag. You can inject the material with a lance, and typically you'll inject it towards the bottom of the ladle and let it float up, and that'll actually pull the sulfur out of the material. A bubble pot or injection with a stirring, it's a wine stall stirrer that'll mix in the material to remove the sulfur. Typically people will desulfurize with calcium carbide or calcium oxide and fluorspar, but the calcium oxide and fluorspar is more on the steel side, or sodium oxide. And the picture on the right here, it just shows, this is a picture of our manufacturing process. We use calcium carbide and the injection and stirring method, and it produces a lot of slag that we have to remove before we make our castings. So moving on to magnesium treatment, you have to make sure that the iron is treated properly to ensure that your graphite changes from a flake graphite form to a nodular form. Typically people use magnesium. You can use other things like cerium and lanthanum, but those are a little bit more costly. But the treatment method's dependent on the material that's being used. So with magnesium ferrosilicon, that can be a blend of magnesium and then ferrosilicon, and a couple other elements can be thrown in there. But typically with magnesium ferrosilicon, you're going to use a pocket ladle. You may use wire feeding. The wire feeding can allow for a higher content of magnesium to be added to the ladle. The sandwich method, or you can actually treat in mold with magnesium ferrosilicon. But either way, in any of these methods, you're using a lower content of magnesium that's not pure mag, and it's typically mixed with that ferrosilicon. A really popular method is either pocket ladles or the sandwich method combined, where you have your magnesium ferrosilicon at the bottom of the ladle, you have a cover on top of it, you pour into the opposite side of the ladle and then allow it to fill, and then that way you have iron covering the magnesium as it treats to improve your recovery. You also can treat with pure magnesium. That's what we do here. So we actually plunge pure magnesium into a ladle that's been sealed off and pressurized, and it's just a different way of treating it. We see a much longer magnesium fade because of that, so we don't see near as much fade as what a lot of people see with things like the sandwich method. But you can also use a tilt ladle, so that's where you put the magnesium on one side, you actually turn the ladle on its side and it's sealed, and it allows the magnesium to treat the iron. So after that, you pour your casting. You can pour into a permanent mold or a sand mold, and then you have to allow the casting to cool, and then you potentially have to do a heat treatment based on the type of microstructure that you want. So the heat treatments, they can be in mold. You do a slow cooling to allow your carbon to migrate and you get a ferritic structure, or you can allow the casting to cool quickly and put it in a furnace at a set temperature and a set holding time and even a set cooling rate to change the microstructure that surrounds the nodules. So here at ASIPCO, we actually do a two-step annealing process. We take our material up extremely hot to dissolve the carbides, and then we'll reduce our temperature to form ferrite and allow the perlite to dissolve. Here are 4 pictures and 4 graphs of what those heat treatments might look like. So on the left, you have a fully ferritic microstructure. On the second from the left, you have a perlitic microstructure. On the third image, you have a martensitic structure, and then on the fourth image, you actually have an austempered structure. But you can see the dotted lines on the graphs below show what a typical heat treatment cycle would look like for some of those. So, you know, on the ferritic structure, you have a slow cooling. On the perlitic, you might have a little bit of a faster cooling cycle. And then when you get into the martensitic and austempered, you might actually have to reheat the material to then cool it correctly the way you need to form the correct microstructure. But with ductile iron and any of these microstructures, you're going to be measuring your nodularity and your nodule count. So your nodularity is how round those nodules are, and that gives you an idea of the quality of the ductile iron. And then you will also do a nodule count. Your nodule count's based on your inoculation that happens after your magnesium treatment. The more inoculation that you have, typically the higher the nodule count. But overall, the better the nodule count, so the higher the nodule count, and the better the nodularity, so the more round the nodules are, the quality of the ductile iron is typically better when those are higher. So that's all I have on the basics, which is very basics of ductile iron manufacturing. I would highly suggest, if you're interested in this, purchasing the ductile iron handbook. It's very very informative for ductile iron manufacturing and has a lot of the things that I touched on. But thank you for listening, and my contact information is there if you have any questions. All right, bye-bye. All right.